What we are going to talk about today are the concepts of linearity and superposition. So most circuits textbooks only teach about the concept of superposition. Superposition is actually a small part of the whole of linearity, and I like to talk about both because the concept of linearity is a very powerful circuit analysis tool in and of itself, even though it's not traditionally applied in that way. Now, one thing that I'm going to do here, which is potentially going to be a bit confusing to some of you, is that I'm going to develop the idea of linearity in a general sense. So instead of looking specifically at circuits, we are going to look at systems having inputs and outputs, and then apply those relationships to circuits specifically. Okay. So let's say that we have a black box system, which could be representative of a circuit. And on the left-hand side is where I'm going to apply my input signals. And on the right-hand side is where I'm going to measure my output signals. So let's generically say that we have an input x1 of t, where this input x1 could be a voltage waveform or a current waveform. So this is just us effectively hooking up a DC source to a circuit. And our black box system acts on this input signal to create an output y1 of t, where y1 of t could be the voltage drop or current flowing through a resistor or something like that. So it's also just a voltage or current waveform. Let's say that we have a second input signal, x2 of t. It generates a second output signal, y2 of t. And the means by which our black box system acts on the inputs to produce the outputs is called the transfer function, h of x. So if our system is linear, and I'm about to hit you guys with literally a bunch of mathematical gobbledygook, and we'll explain what it means in a couple of minutes. If this system is linear, then h acting on alpha x1 of t plus beta x2 of t must equal alpha y1 of t plus beta y2 of t. Or another way of thinking about this is h is acting on a single input x of t and generating a single output y of t, where our total input signal x can be decomposed into parts which are scaled by varying factors. So this mathematical relationship contains two discrete properties. All right. The first of which is the additivity property. and the second of which is the homogeneity or scaling property. So let's talk about the additivity property first. The additivity property is more commonly known, at least in circuit analysis, as the superposition principle. Okay. So additivity says if several independent inputs are used to excite a system, the total response due to all of these inputs can be determined by considering each input separately while assuming all other inputs be zero. In other words, if we have a linear circuit that contains multiple independent sources, we can analyze the circuit with each independent source on by itself to determine our response, be that a resistor current or resistor voltage or something like that. And then we can effectively repeat that analysis for each source on by itself and then add the results together. And that would be the same as us analyzing the circuit with all the sources on at the same time. So I'm going to prove that to you guys. This is going to be the circuit that we are analyzing today. We're going to analyze it a couple of different times in a couple of different ways to illustrate the principles of linearity. So let's say that we have a 6-volt source, a 6-ohm resistor, a 10-ohm resistor which carries a current of Ix, a 9-ohm resistor, and then a 2-amp source like so. So our input signals in this case are our 6-volt source on the left and our 2-amp source on the right. And the response or the output that we are interested in is the quantity Ix. Okay. The first way that we are going to analyze this is to ignore the existence of the superposition principle entirely, okay? So we are just going to analyze this circuit using our current level of circuit analysis. So KCL, KVL, and Ohm's law, and try to develop a relationship to determine the quantity Ix, okay? So I am going to take call it a kitchen sink approach here, all right? I'm going to apply KCL, I'm going to apply KVL, I'm going to apply Ohm's law, and I'm just going to see what sticks and try to get some sort of relationship here. So one thing that I can do to facilitate this approach is to label a few things, right? Actually, let's do that up here. So I'm going to call this current I6. I'm going to call this current I9. I'm going to call this voltage V6. I'm going to call this voltage V10. I'm going to call this voltage V9, like so. So I'm just labeling unknown voltages and currents. So if I were to apply Kirchhoff's current law at my top middle node, I could say that the current I6 is equal to Ix plus I9, and recognizing that I9 is simply -2 amps, I could rearrange this guy and see that I6 minus Ix is equal to -2 amperes. Are we okay with that? Anybody have any problems with our algebra or anything here? So to repeat, all I'm doing is saying by inspection, the current I9, which is the current flowing through the 9 ohm resistor from left to right, is -2 amps, because I know that my current source on the right hand side is pushing +2 amps from right to left. So I9 and 2 amps represent the same current flowing in opposite directions, which is where that negative sign comes from. And I just move the current Ix from the right hand side of the equal sign to the left hand side of the equal sign. Okay, nothing too wild or crazy here. What I'm going to do now is I'm going to apply Kirchhoff's voltage law to my left hand loop. And so that's going to give me -6 volts plus V6 plus V10 is equal to 0, or V6 plus V10 is equal to +6 volts. And now we have two options, okay? So we have two equations with 4 unknowns. Michael, you raising your hand?
What is V9?
So V9 isn't in that Keratos voltage law equation because we're just doing it around the left-hand loop. So if we start here and go around this loop, V9 shouldn't show up. All right, so as I was saying a moment ago, we have 2 equations and 4 unknowns. However, I6 is obviously the current through the 6 ohm resistor. V6 is the voltage drop over the 6 ohm resistor. So those 2 variables are related to each other by Ohm's law. Similarly, Ix is the current flowing through the 10 ohm resistor. V10 is the voltage drop over the 10 ohm resistor. So the variables Ix and V10 are related to each other by Ohm's law. So what I'm going to do is I'm going to use Ohm's law to rewrite this equation, okay? So V6 would be 6 ohms times I6. V10 would be 10 ohms times Ix, and this is equal to 6 volts. And I now have a system of equations. Equation 1 and equation 2. 2 equations, 2 unknowns, which should allow me to solve for the quantities I6 and Ix. So let's use our calculators and solve this system. So when I solve it, I get I6 is negative 7/8 of an amp, and Ix is positive 9/8 of an amp. By all means, take a moment here to verify these results. So the analysis that was involved here, to me, a jackass with a PhD in this stuff, wasn't particularly difficult. But I would argue that this is probably one of the most difficult circuits that you've been asked to analyze to this point, right? You have to apply literally everything you know up to this point in order to analyze it. Okay. So what we are going to do next is we are going to use the superposition principle and analyze the circuit twice, but with the very important caveats, okay? The first time we analyze it, we're going to have the voltage source on by itself, which means we'll have the current source turned off. We'll get a result. Then we're going to reanalyze it with the voltage source off and the current source on, get a result for Ix, and then we're going to add those 2 results for Ix together, with the expectation being that the sum will be exactly 9/8 of an amp. If that is true, then this circuit containing resistors and independent sources would be an example of, we can't say that it's a linear circuit because we haven't looked at whether or not it satisfies the homogeneity property, but we can definitely say that it satisfies the additivity property of linearity. Okay. All right, so method number 2. Superposition. Just going to redraw my circuit here. And let's say specifically voltage source on and current source off for this drawing. So I have my 6-volt source, my 6 ohm resistor, my 10 ohm resistor. I'm going to call this current IX prime, and it represents the contribution of the 6-volt source to the quantity IX. Here's my 9 ohm resistor. And now we need to talk about what to do with our current source. Okay. So our goal here is to turn our current source off. So what does it mean to turn a current source off? Anybody have any thoughts? Say that louder, Sarah. Make it into an open circuit. Why specifically? Well, that's fair. So if we had 2 amps of current, so an off current source would represent a current source that's supplying 0 amps of current. An element that we know must have a current of 0 amps flowing through it is an open circuit, like Sarah suggested. So to turn off a current source, we replace it with an open circuit. All right. So how can we solve for the quantity IX prime in this circuit? Well, argue just Ohm's law, right? So I believe, and by all means, if you do not believe me, let's talk about it, that the current IX prime is simply 6 volts divided by 6 ohms plus 10 ohms, which would be 6 over 16, or 3/8 of an amp. The 9 ohm, yes. We could. So Kirchhoff's voltage law would have said -6 volts plus 6 IX prime plus 10 IX prime is equal to 0. And then rearranging, you would get literally that exact same result. Yeah. The 9 ohm resistor isn't going to show up in our equation here because it's not part of a closed current carrying path, right? So effectively, whatever current is leaving the 6-volt source, all of it flows through the 6 ohm resistor, and then all of it has to flow down through the 10 ohm resistor, which is why I can lump those 2 resistors together. They appear like they are in series because they're carrying the same current.
You couldn't do that if there was like just a short between the 9 and the rest of the circuit, right?
That is correct. If there was a short circuit on the right-hand side, I could not do that. I would have to take into account that the current is able to split. But the open circuit forces the current to not split. So are we okay with our analysis here with the voltage source on and the current source off? Anything particularly wild or crazy?
So IX
We're
prime
going to
is not,
reanalyze the circuit then with the voltage source off and the current source on. So how do I turn off a voltage source? Not Sarah. Anybody have any thoughts? It would be a short circuit, absolutely. So if we want to make 9 volts turn into 0 volts, or we're turning off our voltage source, right? So it had 6 volts originally. Now it should be supplying 0 volts. Well, the element that we know that has a fixed voltage drop of 0 volts is a short circuit. So we replace our voltage source with a short circuit. We leave our current source on. And this is the quantity Ix double prime, which represents the contribution of the 2 amp source to the quantity Ix. To me, the easiest way to determine this current Ix double prime would be to apply current division, because we know that there is a current of 2 amps flowing into the parallel network containing the 10 ohm resistor and the 6 ohm resistor. So Ix double prime would be 2 amps times 1 over 10 ohms divided by 1 over 10 ohms plus 1 over 6 ohms. So let's see, that's going to be 3/30 over 3/30 plus 5/30. So that's going to be 3 over 8 times 2 is 6 over 8 amps. By all means, throw that in a calculator if you don't want to do the math in your head like I do. And using these results, we find that Ix is equal Ix prime plus Ix double prime is 9/8 of an amp. So we get the exact same result as we got in our previous analysis, despite the fact that we're analyzing the circuit only with one source on at a time. So this guy absolutely obeys the principle of additivity. So what I'm about to do here is I'm going to write down a little bit of a table, and we're going to kind of carry this table with us for the rest of our analysis today. Okay. So on the left-hand side, I'm going to put inputs, and on the right-hand side, I'm going to put output. We have observed that when we have a 6-volt source on and the 2 amp source on, our output was 9/8 of an amp. We have observed that when the 6-volt source is on by itself, our output was 3/8 of an amp. And we have observed that when the 2 amp source was on by itself, our output was 6/8 of an amp. What we're going to talk about now is the scaling or homogeneity property. Property. All right, so the homogeneity property says if an independent input is used to excite the system scaling that input by an arbitrary factor of alpha causes the output to scale by the same amount. So what we are going to do is we are going to scale both of our inputs by a fixed scaling factor of 2, okay? Meaning that my 6-volt source will become a 12-volt source. And my 2 amp source will become a 4 amp source. I'm going to call this guy I6 again. Then we're going to have this voltage V6 and this voltage V10. If I apply KCL, I find that I6 minus IX is now equal to -4 amps. And I know that 6 ohms times I6 plus 10 ohms times IX is now equal to 12 volts. I'm going to solve this system for I6 and IX. And I get -7/4 of an amp for I6 and positive 9/4 of an amp for IX. So if I scaled my inputs by a factor of 2, did my output scale by a factor of 2? Absolutely. So I'm going to take my little table here and I'm just going to make a copy. So let's just move it down and continue to record our observations here. Okay. So what we have just seen is that when I apply twice 6 volts plus 2 amps, I get 9/4, which is exactly twice the output of when I applied just 6 volts plus 2 amps. Okay. So our last thing to do here, so we have observed that this circuit obeys the property of additivity, and it obeys the property of homogeneity. For it to be a linear circuit, it must obey those 2 principles simultaneously, okay? So what we're going to do is we're going to scale each of the inputs by a different factor and consider what would happen in those cases, all right? So let's say that we scaled the voltage source by a factor of -3. So if we applied put my stylus right. -3 times our 6-volt source. What would our expected output be with just the voltage source on? -9/8, right? We would just multiply the output when the 6-volt source was on by itself by a factor of -3. So absolutely right, -9/8 of an amp. If we scaled the current by a factor of +5, what would our expected output be with just the current source on? 30/8. All right, and finally, if we do these simultaneously, what do we expect our output to be? Just add those results together. -9/8 plus 38 is 21/8, right? So what we're going to do is we're going to analyze the circuit under those constraints and verify that our expected output of 21/8, which we got by applying the homogeneity and additivity properties together, match the behavior of our circuit. If so, then this circuit is an example of a linear circuit. So our voltage source is an 18-volt source, positive polarity on bottom, because that's what happens when we scale it by a factor of -3. The amplitude gets 3 times as large, and we swap the polarity because of the negative side. Here is our 6 ohm resistor. Here's our 10 ohm resistor through which a current IX flows. Here's our 9 ohm resistor. Here is our 2 amp source. Just defining our current I6 and our voltages V6 and V10 again. When we apply Kirchhoff's current law at that top middle node, we'll find that I6 minus IX is equal to -10 amperes. And when we apply Keratos Voltage Law around our left-hand loop, we'll find that 6 ohms times I6 plus 10 ohms times IX is equal to -18 volts. And we will now solve for I6 and IX. And I get I6 to be -59/8 of an amp, and IX to be +21/8 of an amp by solving that system, which matches the result that we got by applying no circuit analysis whatsoever. Eric. Oh, I'm sorry. So that's my fault here. So this shouldn't have been 2 amps. This should have been 10 amps because this was supposed to be scaled by a factor of +5. Thank you for noticing that. Michael, was that your concern as well? Great. Thank you both. All right. So we have found that this circuit containing independent voltage source, an independent current source, and resistors is an example of a linear circuit because it obeys the additivity property and the homogeneity property simultaneously. Any circuit that contains independent voltage sources, independent current sources, resistors, capacitors, and inductors is an example of a linear circuit. Okay? If it contains dependent sources, that's really kind of an interesting thing about sources. Sources aren't inherently linear or nonlinear. They just depend on what they are connected to. Okay, so really, if the circuit contains resistors, capacitors, and inductors, as long as those resistors, capacitors, and inductors are not time-varying quantities, then we have a linear circuit. And if we have something like a photoresistor whose resistor value depends on some external stimulation, that would be an example of a nonlinear circuit. Diodes and transistors are inherently nonlinear as well, which we're not going to talk about in this class at all. Okay. One thing that wasn't mentioned here, though, was dependent sources. If we looked at all of our descriptions, it only mentioned what to do with independent sources. Okay, so let's work one quick example, which I'm just going to make up here because I didn't bring one. Let's say that we have 5-volt source, a 3-ohm resistor, a 2-amp source, a 10-ohm resistor, and then a dependent voltage source twice Vx, where Vx is defined to be the voltage drop over the 10-ohm resistor, positive polarity on the left. Okay. So let's say that we are going to try to analyze this circuit using the superposition principle, okay? Meaning that we were going to analyze it with the voltage source on, current source off, then again, voltage source off, current source on. The dependent source will always be left on. We can never turn a dependent source off, okay? So if our goal here is to determine the quantity Vx with voltage source on and current source off, this circuit would look like this. Here's our 5-volt source. Here's our 3-ohm resistor. Here is our 10-ohm resistor. Here's a quantity 2Vx prime, where this is our voltage. Vx prime. Since this is an example of a single loop circuit, we would probably just apply Keratos Voltage Law and find that, let's call this current I, so that we would have 5 volts is equal to 3 ohms times I plus 3 Vx prime, where Vx prime is simply 10 ohms times I from Ohm's law. So we would have 5 volts is 3 ohms times I plus 3 times 10 ohms times I would be 5 volts over 33 ohms. And from this Vx prime, which is 10 ohms times I, would be 50 over 33 volts. Okay. So the voltage drop over the 10 ohm resistor is Vx prime. And then there's a dependent source supplying 2 Vx prime, and I added them together to get 3 Vx prime. Because when I apply KVL, I add voltage drops. I could have said it's 5 volts is equal to 3I plus 10I plus 2 Vx. And then I would have made that exact same substitution for Vx prime using Ohm's law, and I would have gotten literally the exact same result in my third equation. So 6 of one, half dozen of the other. Whatever you're more comfortable with, I'm okay with. We would then need to reanalyze the circuit with our voltage source off and current source on. So we'd have 3 ohms, 2 amps, 10 ohms, 2 Vx double prime, like so. And this guy here looks a little tricky. Sorry, I should put my negative polarity. It looks a little tricky to solve using our current level of circuit analysis knowledge. Let me think just a moment on how we might go about doing this. All right, so let's say this is I3, and this is I10, so that I3 plus I10 is equal to 2 amps is one equation. And we know, applying Kirchhoff's voltage law, 3 ohms times I3 is going to be equal to, so that's the voltage drop over the 3 ohm resistor, is going to be equal to 3 Vx prime, where Vx, double prime. Vx double prime is just 10 ohms times I10. So that's going to give me 3 ohms times I3 minus 3 times 10 ohms times I10 is equal to 0. Here's equation 1. Here's equation 2. We can solve these guys to find I10, and then we would substitute I10 into our Vx double prime relationship. So I get I3 to be 20/11 amps and I10 to be 2/11 of an amp. Substituting that in here, Vx then becomes Vx double prime is 20/11 of a volt. And finally, Vx is Vx prime plus Vx double prime. So that is 50/33 plus 20/11 is 1/3 of a volt. Anyway, all I really wanted to do with that was illustrate that you need to learn, or excuse me, you need to leave the dependent sources on always whenever you're applying superposition theory. All right, so there's an in-class assignment that I want you guys to do, and I want to look at it really quickly to help explain something. Open. So in part A here, when I say determine the contribution of the 1 amp current source to the voltage Vx, what that means specifically is leave the 1 amp current source on and turn the other source off. Similarly, in part B, when I say determine the contribution of the 5-volt voltage source to the voltage Vx, that means leave the 5-volt source on, turn the current source off. Part C, add the results of parts A and B together. Part D, do that scaling trick like we did at the end of the reworking that circuit over and over again. Do not actually go through and do the analysis. That's the beauty of the superposition principle. You don't have to redo any of the analysis. If I want to scale, so if I scaled, if the 5-volt voltage source were replaced by a 3-volt source, that means I'm scaling it by a factor of 0.6. Positive polarity on bottom means I'm scaling it actually by a factor of negative 0.6. If the current source is replaced with a 2.5 amp source direction up, that means I'm scaling the current's contribution by a factor of 2.5 amps. So effectively, you just take the result from part A, multiply it by a factor of negative 0.6, add to that the result of part B multiplied by a factor of 2.5, and you are done. You do not need to do the circuit analysis, okay? The only actual analysis that I'm asking you to do is in parts A and B. Now I want to look very briefly at the web work set. I think I have to put in my credentials here. Oh, okay. Homework set number 5. All right. That is the wrong class. Yeah. We haven't gotten to op amps yet. My apologies. All right, this first problem has nothing to do with superposition whatsoever. So let's move along. This problem is all about the homogeneity property. Even though I don't think any of the other circuits teachers actually teach the homogeneity property, this one is very easy to do. Inasmuch, if you solve part A, then you know the answer to part B just by scaling things. Or if you solve B first, then you know the answer to part A just by scaling things. And then C is simply the ratio. So this can be trivialized by just solving it once and then using the scaling properties to get the other results that you want. Problem 3. In my opinion, it is unfair that this problem containing 3 circuits is only counted as one problem because it's actually a lot of work, okay? For part A, that's actually a good place for you to practice applying superposition principle, okay? Circuits B and C are terrible for that. Let me explain why. You're going to have to set up, because of the dependent sources, you're going to have to set up a system of equations to solve either of those. What we are going to learn in Wednesday's class is nodal analysis, which is setting up a system of equations to solve for unknown voltages. What we are going to learn in Friday's class is mesh analysis, which is effectively setting up a system of equations to solve for unknown currents. So I would argue that if you're going to have to set up a system of equations to solve the circuit, you should use one of the methods where that's the desired intent. So in my opinion, part B and part C, you should hold off on until we cover nodal analysis, because that's a much easier way to do it. So this doesn't, in my opinion, B and C here do not reinforce what I'm trying to get you to understand using superposition. They are unnecessarily difficult using that method. So I would highly suggest you skip them for now. Problem 4 is a very reasonable superposition problem, okay? So to recap, problem 2 is all about the scaling property of linearity. Problem 3A is a good place to practice applying the superposition principle. And problem 4 is a good place to practice applying the superposition principle. 3B and 3C, leave them alone until we learn a more powerful analysis tool that will trivialize those. Because it's taking 15 plus minutes of work down to 3 minutes of work if you wait until Wednesday's lunch. All right, that's enough out of me. Yes, sir. Yes, it is not unreasonable to assume that all of the circuits in this class will be linear circuits, so that superposition is a fair game analysis tool. 100% right.